Hi, everyone. We have already explored together that we can head right into Desmos. We can speed up the process. Just write normal, dist, and parens. And then as soon as we do that, it's going to lock and load us with a standard normal distribution, which is to say a normal distribution whose mean is zero. It's centered on zero, and we see that, and whose standard deviation is 1. But what this doesn't show us at all is what this has to do with that PDF formula, and I want to do that together and build it up from scratch, as it were. Here was that PDF formula. The PDF is a function of the continuous random variable x. X is our one continuous random variable that can take on any value from negative infinity up through infinity. We get the two parameters sigma, which shows up twice, we'll get there, and mu, the mean, which shows up once. Remember, e is not a variable, it's a constant. Pi is not a variable, it's a constant. So everything else here is fixed. We've got one variable, x, and we've got two parameters, mu and sigma. Let's build this up from scratch. I'm going to start off with an exponential function, y equals e raised to the x, and this behaves the way we would expect an exponential function to behave. It collapses to zero as x gets smaller and smaller, or more and more negative. It explodes up to infinity in a big hurry as x gets larger and larger. That does not look at all like a normal distribution. I think you'll agree. What if we do this? Y equals e raised to the negative x. Well, that's just a reflection of what we had before. Now y is getting really big as x gets negative, and y is getting arbitrarily close to zero as x gets larger and larger. That's not really doing the trick, is it? But that doesn't look like a normal distribution, and it's having some combination of the two of these. Let's kind of monkey around a little bit and see if we can fix this up. Remember our PDF, there's this square term. There's a negative term, but there's a square term. Let's just see what happens if we add the square bit. Y equals e raised to the x squared. That's the green one. Well, that's getting large in both directions, and it's doing so in a big old hurry. Okay, that's not quite right. Let's try one more thing. Let's go y equals e raised to the negative x squared. And wouldn't you know it? What does that look like? That looks a heck of a lot like our normal distribution. In fact, that looks exactly like our standard normal distribution at first blush. Now, if you remember, our standard normal distribution, it peaks out right at around 0.4. See that? That's our standard normal distribution, and it gets up to like zero point 0.4. Remember, it's the area under the curve that has to equal 1. In fact, if I say find the cumulative probability from negative infinity all the way to infinity, in other words, the area for everything under the curve, we get exactly 1. Well, I don't know. I mean, it looks like it's got the right basic shape, but it kind of looks too tall, right? Maybe we got to do something about that. As a first blush, let's go y equals 1 divided by the square root of 2 pi times the rest of this. Copy paste. And now it still has all the same shape. It's still centered at the same place, but this is looking a lot more like what we've seen before, kind of peaks out at around 0.4. That's a good sign. What we're going to do is we're actually going to calculate it. We are going to take the integral from negative infinity to positive infinity, and you don't need to know too much about what that means. It's just a way of calculating the area under our respective curves. We'll start off and we'll say integral, or int, and then we'll negative infinity up to infinity. We'll kind of go with the first one because, that looks so promising. And we always have to put the dx at the end when we're taking an integral. And that's too big, isn't it? It's that 1.7724. It goes on and on. What would happen if we took that little piece and put it out front here? Well, now it's too small, but it's looking better. There's something missing. Hopefully you can see it. Remember in our original PDF, we had this -1/2 out front, right? Now we still haven't dealt with the parameters. We haven't dealt with the standard deviation, the sigma. We haven't dealt with the mu. We're just trying to get the area under the curve of this darn thing to equal 1. And let's just see what happens if we do 1/2. Bada boom, bada bing. We are exactly at 1. Not only does it look normal, but it also has the area under the curve equaling 1 the way we were hoping that it would, that it should. This officially makes it a probability distribution. Let's just see what happens if we mess around with this a little bit and deal with those parameters, the mu and the sigma. I'm going to put in parentheses x minus 3, and we know that that would center the new distribution on 3, as it were. I'll show you that. I'll kind of come up here, and we'll subtract 3, and there you go. We now have a normal distribution centered on 3. And it looks like that didn't do anything to the area under the curve. The area under the curve is well behaved. It's 1, just the way that we wanted it to be. Let's see where the sigma comes in. Well, hey, we've got the sigma down here in the denominator. So if we want a larger standard deviation, we can just kind of put that down in the denominator of that PDF, and let's experiment. Let's see what happens. I'm going to move this out. I'm going to put in a division, x minus 3. That's all good. And then I'm going to make a standard deviation of 4 and see what happens. When I put in 4, the area under the curve is now 4. That's too much, right? What I need is for it to be 1/4 of that. And if I put the same value down here as lives up there, the area under the curve now goes back to 1. Here, just to show a picture of what's happening. Okay, well, we got this 4, and then I put the 4 out there, and the area under the curve is 1. We can do the same thing. Well, what if I did 0.333 and 0.333? Okay. Well, now all of a sudden I have a normal distribution, and let's see what happens if I match them. 0.333, well, that's too small, isn't it? What if I do 0.333? The area under the curve is exactly 1, which is what we need to see at all times. We have together built from scratch the PDF in Desmos, and we can see why it looks the way it does, both the PDF as well as the actual visual of the normal distribution, the bell curve.